Well, okay, let's continue. This is the final day, so thank you very much. Please carry on.
Okay, so today, I kind of want to put the pieces together and to present results which are actually from a paper with Dominic last year. So in the previous lectures, I've been kind of trying to give you heuristics, kind of models, kind of ideas, kind of emerging from kind of looking at the Nash embedding theorems from the probabilistic point of view. And the previous lectures, it was kind of like, how do you make the embeddings? As I said, at this point in time, we don't have probabilistic proofs of Nash's theorems, even though that was kind of where this work originated. But along the way step, there were many heuristics, hints, other ideas which kind of show how probability theory is natural in the problem. So probability theory is natural for the definition of the metric. Probability theory is natural because there's a kind of stochastic analog of the Nash lemma. Probability theory is natural because heap kernel embeddings are used in machine learning. Probability theory is natural actually from the mathematical physics standpoint because it turns out that the embedding problem has a precise analog in physics called the nonlinear sigma model. So kind of in that world, we're trying to put down Gibbs measures, and again, probabilistic reasoning is fundamental. So somehow these ideas were kind of building up. Last year or kind of last year and a half, it kind of crystallized and kind of, okay, here's a kind of foundational place where you see a tight relationship with the isometric embedding problem and kind of probability theory. And it's a fundamental space. It's actually the construction. So what I would like to do today is to actually discuss kind of connections between the isometric embedding problem, where our results are all from analysis, and the problem of the construction of Brownian motion on the Riemannian manifolds. So somehow in this world, what we've been trying to do is to present to you a modern take on the results of Nash mainly from 1954. But today I'd actually also like to add on the role of Nash from 1956, the smooth embedding paper. The construction of Brownian motion on Riemannian manifolds is a very fundamental problem in probability theory. The first works in this area go back to Ito's idea of stochastic parallel transport. And so here there are many results which are obtained in the 1970s, and a kind of very comprehensive and really for us kind of very inspiring source of this material is in the book of Ikeda and Watanabe. And I just looked it up. I think it's chapter 5 or chapter 6. Okay, so it's a kind of very very powerful chapter actually. Which presents several ideas on how to make Brownian motion. Not just, it's really diffusion process on manifolds. And I feel like even when I'm looking at that chapter, we're only seeing parts, the early parts of that chapter. So what I would like to do in some sense is to kind of look at both of these ideas together and to give you a collection of results. And so all the references today for the talk today, the primary reference is a paper that Dominic and I wrote and posted on the archive last year. So the title of the paper inspired very much by local theory, even though our study of this problem is really kind of at its basic stage, but really it was kind of inspired by the construction of SME and ideas of that nature. And so this paper is posted on the archive. Of course, you can just Google it, but let me give you the locator.
Yeah, I think Sarah sent it.
Okay. Okay. Not quite sure. Okay. I have this in front of me, so I feel like, since I'm being recorded, I should write it down. Okay. Yeah.
I mean, it is same.
Sorry, what? Okay.
No, it's something about it, so.
Okay, fine. Why don't you guys resolve it and then.
¿Sí pueden leer desde ahí? los de Zoom? Sorry.
Sí,
Ok, gracias, sorry.
Okay.
Sí,
all good?
sí se ve.
Ok, gracias.
Are you recording or not recording?
Yes, we are.
Oh, okay,
Yeah,
fine. Okay.
They can read.
Yeah, okay. So is there a threshold on that side?
No. Do as
Okay.
move as you want.
So what I'd like to do, I mean, the paper has all the details, but there are a couple of things that I would like to do. So there are a couple of places in the paper where I feel it's kind of like it's kind of feels like maybe slightly technical things that we were not able to do. So one is kind of involving semi-martingales, the other one is kind of involving a tightness estimate. And I think these are places really where we greatly appreciate people looking at it. So in kind of the spirit of which I've been giving the talks, I'll try to kind of give you the ideas and the motivation based on kind of both the conversations and the lectures so far. So what I first want to do today is just to kind of give you a construction of exterior grounding motion, just to define it and tell you how this idea crops up in our work. And then to kind of state, in some sense, the main results, which are kind of, let's say, the equivalence of the isometric embedding problem, which is this analysis problem. And the construction of grounding motion. So in some sense, this is the main insight, but the insight is not quite enough. The insight is not quite enough. You really have to get the details right. And I think this is why, in some sense, it was, I think, so important that each of you saw the kind of details that go into NASH 1954. Okay, so let me just begin by actually giving you what I mean by exterior boundary motion. The exterior. Wait, I don't want exterior. Okay, sorry, I had too much coffee today. Extrinsic grounding motion. So let me begin by kind of introducing you to extrinsic grounding motion, which is a way of constructing grounding motion on a Riemann manifold. So let's begin with that. So question, how do we construct? So as in the previous lectures, we will just assume that M is compact, or M is closed, compact the boundary, so that there are kind of no technicalities to worry about. And so just at the very outset, when we're speaking about the construction of grounding motion, of course, this is a problem that can be approached through so many different forms of limit theorems. I should stress that what we're interested in is hands-on constructions using stochastic differential equations. So the spirit is, can you write down a stochastic differential equation so that you will construct the grounding motion?
Yeah, the martingale problem is not good approach.
I will get to that.
Okay.
So there are. I'll first kind of give you a sense of how things were done in the work of Ikeda and Watanabe and in the kind of preceding work. And to cut a long story short, what's basically happening is the following. So what we've shown you is that in the isometric embedding problem, there is this phenomenology involving the codimension, the smoothness of the metric, and the smoothness of the embedding. So just geometry forces you to look at rough embeddings. When one looks at the traditional theory of stochastic differential equations, so for example, in the books of Ikeda Watanabe, Strouk, or the book of Elton Su, somehow, look, I mean, you're kind of putting together two very different areas of mathematics. You're putting together Riemann geometry, and you're putting together stochastic differential equations. And so in all the work, it is always conventional to not make any smoothness assumptions on the metric, except to say that the metric is C infinity. So the real contributions in our work are kind of putting these pieces together and pushing results towards low regularity. So low regularity phenomena is critical in our work. And so I kind of want to show you how, in some sense, in the construction problem of grounding motion on MG, just in this extrinsic grounding motion construction, you immediately see kind of the low regularity phenomena and the need for studying low regularity phenomena. And so that's kind of, let's say, the best motivating point, I think, for a general discussion Though of course, in our worldview, there were kind of a whole bunch of other reasons for trying to look at these critical exponent phenomena. Okay, so how shall we do this? So let's first do this. So let's look at only C infinity metrics and C infinity embeddings. So that really puts us in the regime of Nash 1956. So though we haven't kind of stated this result with precision, let me just kind of state it somewhat informally, because it's the foundation for this particular construction. So assume given a manifold that G belongs to C infinity. Let me actually be that means so carefully organized. So five.
Günther has maximum of n star plus n plus 5 and I stopped writing.
And you stop writing at that point. So I think the maximum of, okay.
But I can tell you, Nash has q bigger than or equal to n times 3n plus 11 divided by 2.
Okay,
that's Nash.
So there's what did you say it was?
N times 3n plus 11 divided by 2. If the manifold is called.
So take your given manifold, it's an n-dimensional manifold, and we'll map it into a very high dimensional space. There exists this metric embedding. So, okay, so let me write it out this way. There exists an embedding such that
And he was smooth. Seems smooth.
there exists. Okay, very important here. So, thanks to Nash 1956, which is actually a pretty high-powered theorem, in some sense involving kind of deeper technicalities than in Nash 1954, we know that there exists a smooth embedding. Okay, so it's a profound result because it really reduces. So one way of thinking about the Nash theorems is that you're actually reconciling two different notions of space, two different notions of manifold. One is the classical 19th century notion of a manifold as being, let's say, an embedded hypersurface or generalizations thereof. And the other one is the 1936 definition of Whitney, which basically kind of describes a manifold in terms of kind of a second countable Hausdorff space batched together. So somehow formalizing the idea that the manifold is a space that locally looks like a Euclidean space. So what one can do to make Brownian motion a manifold is to recognize that here we have a standard space, RQ. We know how to make Brownian motion on RQ. So let us start out with Brownian motion on RQ, and from that, construct Brownian motion on the manifold. Okay, so in kind of a cartoon, so we've got our abstractly defined n-dimensional manifold here. We have got a mapping of this manifold into Euclidean space. And some holes in there, although that doesn't feel like a real manifold. And on the space, So given any point in the space, we know that there is a standard Wiener process on the space. So the other natural thing that you want to do is to take this Wiener process and essentially project it onto this manifold in order to construct a stochastic process on this manifold, which would correspond to which if you pull it back over here would correspond to diffusion. So let me call that CT, and let me pull that back. So since it's an embedding, it's a one-to-one map. It gives me a process over here. So what you want is XT diffusion on with the generator and so somehow what you have is this stochastic process. And so what you would like is to write out an SDE for a process over there, the ZT, and kind of bring that back and get a process over here on the manifold. In some sense, maybe you don't even want to distinguish between kind of like the original space and that space and just focus on the embedded object and to write out an SDE on the embedded object. So once one has conceived of this idea, there is a canonical geometric recipe so let me introduce a notation that we will use a few times. So let's call this space. So let's denote the image of the manifold by sigma. So that's sigma. And sigma, I can, so this is the since we're doing isometric embedding, so you've got, if you've got a smooth manifold sitting inside the space, as we've discussed many times, the smooth manifold acquires a metric because it's embedded within the Euclidean space. So it's just giving my inclusion in RQ. And so if I want a Brownian motion, which begins at some point, some marked point X, let me look at the image of X to be a marked point little z. And the natural SDE that you write down is, okay, so let me make a definition. So let's let me make a slightly different picture of sigma. So that's my space sigma. Let me pick my point Z over there. Let me look at the tangent space at the point Z in sigma. And let P of Z be the orthogonal projections. We've seen this yesterday when I kind of introduced geometric construction of Dyson-Brownian motion. So it's tangent space at the RQ. Yeah, it's the sigma to be orthogonal projection. So the orthogonal projection or orthogonal projection is one of the most natural things that you can do with any geometry. And so now what we're going to do is to just write out how we do the projection of the standard driving noise onto the manifold to get an SDE and for SDE. So let me call this equation actually E for extrinsic. Let's look at the initial conditions. V0 is equal to C. This is a Stratanovich And if you go back and look at, so this, for example, this construction, so this way of making extrinsic Brownian motion can be found, for example, in Elton Sue's book or in a chapter in Strook's book on, what's the title of Strook's book?
Several.
No, it's like Strook has a book on the geometry of path spaces on Riemannian manifolds. So it's really about stochastic differential geometry. And so there's a chapter in Strook's book which is really about this construction. Okay, so the construction over here is very, very natural. Perhaps a little bit, if you're kind of used to Ito SDs, it's a little bit unfamiliar at first sight. To begin with, it's Stratonovich SD. But you want to use Stratonovich SDs whenever you're doing stochastic calculus on manifolds. You really want to work with Stratonovich because you want the standard change of variables. And you want the standard change of variables because whenever you're doing manifolds, you always want to ensure that whatever you're doing, your calculations are independent of the coordinate system. So you use Stratonovich so that you get the chain rule, and since you kind of have to have the chain, and you have to have the chain rule in order to respect coordinate invariance. Okay, so the construction is that solves this SD, given some initial point, and the solution to this SD is going to be the desired Brownian motion. So let's try and understand this SD better. And now, since our points are in RQ, let me actually state this as a theorem. So it was a big deal for me when Dominic showed me this, but of course, terms of this nature are fundamental calculations of this nature are always known when you discover them. But here's a theorem due to Lewis. Sorry, was there a question? Yeah. Question? Okay. So just a way of understanding this SD better in terms of fundamental, let's say fundamental geometric intuition. So here's a theorem due to Lewis, who's a British probabilist. I'm quite sure which year. One would be. Six. The Brownian, let me just write the SE is equivalent to the Ito SD. dVt is ejection dT dWt plus 1/2 h of the gt, where h dt, h of the is mean curvature of sigma. So there's a standard conversion formula that takes you from Stratonovich SD to Ito SD. And one of the reasons I like this formula so much is it kind of gives you, first of all, a natural intuition. And for example, even a numerical scheme for how to simulate Brownian motion on an embedded manifold. And let me kind of just make this as a remark. So intuitively, let's think about the curvature or mean curvature as a constraining force. Or 1/2 would be even minus 1/2 mean curvature. So what I mean by that is like, let's think about just a one-dimensional curve. And I want to make Brownian motion on this one-dimensional curve. And so, one of the ways you kind of want to think about Brownian motion is always by kind of thinking about a random walk. And so imagine that you were sitting at this point and you have So, you're making Bradley motion on this manifold, so you're kind of taking a random step. So this piece over here, you want to interpret as a random step. So if you just integrate a little bit of time, imagine that you're taking a random step in the tangent direction. And then you have to do a projection down. So you want to make a random walk on this curve. You want to make a random walk on the curve, taking kind of random steps in the ambient space. And so somehow you begin to see that curvature must come in, because curvature must come in to keep you on this manifold. So that, of course, is you may find this kind of far too imprecise, but I was brought up as an engineer, so this is kind of how you're trained to think. But the real precise theorem over here is really just that this is the fundamental way, a fundamental and intuitive way of trying to make Brownian motion on the manifold. And you work out the calculations, and kind of what's coming out is that the curvature is the correction. So somehow it's a nice fact that you start out with a geometrically natural SDE. And what comes out is kind of that the drift of this SDE is something which is geometrically very, very natural. So this is quite important and kind of really fundamental for the way that we're thinking. So our goal in general in these problems is to achieve geometric theorems from strictly probabilistic hypotheses. So that's what I was trying to kind of push in lecture by lecture, right? Okay, think about distance itself as a probabilistic entity. And so here, what this theorem is actually allowing us to do is, if you toss out all of this picture, what it's really telling you in some sense is that you can think about curvature on strictly probabilistic grounds. Okay, so over here, what we're really doing is we are building a probability measure on path space. And what we're understanding is that the compensator over here for this probability measure, for this diffusion on the spot, for this probability measure on the spot space, is really something geometrically fundamental. So to cut a long story short, kind of tell you the kind of fundamental conjecture that we have, and kind of along with results that go with this, is that what I want to do next is to actually try to ask ourselves, or to kind of push into the low regularity regime, to not use Nash 1956, but to start with Nash 1954, and to ask if one can do this construction again. Let me just pause for a second. Is the story up to this point clear? Okay, so what I've said is we want to make, so today's lecture is all about construction of Brownian motion on Riemannian manifolds. And what we're doing over here is kind of providing a general recipe for the construction of Brownian motion on Riemannian manifolds. And at the heart of this general recipe is our understanding of Brownian motion in Euclidean space. So you start out with Brownian motion in Euclidean space. You want to get a good SDE for Brownian motion in your Riemannian manifold. And in order to kind of close the story, you need this extremely heavy hammer, which is the Nash embedding theorems. So if you assume Nash 1956, which is a kind of high power theorem, then you get for free Brownian motion on the manifold. Okay.
I'm not that sharp on geometry. So if I have the tangents, and I have the H's, how much does that determine the metric?
I don't know how to address the question. The metric is not determined by the first and most, one of the fundamental things is this is an extrinsic curvature. So it's a property of the embedding. So the way you want to think about curvature in this case is that what's really going on is the first, okay, let's do C1 and C2. So if the first derivatives of the manifold are giving me the tangent vectors, first derivatives of U, the second derivatives of U are giving me the change in the normal vectors, and curvature over here is corresponding to the change. So each normal vector, so imagine taking curves, so imagine taking different curves on your manifold and seeing how the normal vector changes as you go. And so somehow the mean of those changes, shall we say, intuitively, is what's giving rise to the curvature. So the mean curvature is really a function of the embedding. The metric itself is coming from only the first derivatives of the embedding.
Okay.
Now, it's a very important point because it really relates to the smoothness of the embedding. Okay. So this SDE is going to be well defined only if this SDE is well defined. And this SDE is well defined depending upon how smooth the sky is. Right, so if you go back to basic SVU theory, you want this to be a Lipschitz function of your point Z.
It's okay.
Okay, so it's kind of like, okay, no, let's do this really carefully, right? Because this is kind of very important. So Z is this point that's living on this manifold, and h of Z, at each point on this manifold, I've got a function h of Z, vector valued function in the normal direction. And the way I get this function h of Z is by doing the trace of the second fundamental form, but really just think about it as I need the second derivatives of U to compute curvatures. Okay, it's the change in normals. Really just think about a curve, see how the normal goes. That gives you a feeling for the intuition. So if you take a sphere, have like one, you have all of the curves that kind of go on the sphere, and you see how the normal changes, and you'll pick up exactly the radius of the sphere.
Yeah, I shouldn't have asked about G. I should have asked about G and U.
Yeah, sure.
I have a question, sorry.
Yeah.
And here Nash 56 is coming into play through the fact we can embed isometric.
Yeah, absolutely.
Q and H is very well defined.
Right. Yeah, absolutely. So this construction, you can criticize it in several ways, as it was in the 1970s. So the criticisms are, first of all, that the criticism is fundamentally that everything that you're doing is extrinsic, whereas with a manifold, you somehow really want to do things in an intrinsic way. So the criticisms are, at first, on one hand, that like conceptually, you're doing something extrinsic when really with a manifold, you just want to think intrinsically. The criticism is that maybe you're using too many different, you've got an n-dimensional manifold. So if you want to describe Brownian motion on this manifold, in some sense, you want to use n Brownian motions, not q Brownian motions. So we're actually sitting in a high dimensional space. And finally, the criticism is that Nash 1956 is a very tough analytic theorem. And so using this very high-powered theorem to actually address something which, as probabilists, you would feel like Brownian motion should have a much, much simpler description. So in fact, this is all true. And in the 1970s, a completely different construction of Brownian motion was put forward, the intrinsic construction of Brownian motion by Eels, Elworthy, and Mullivan. But before coming to that, let me actually give you a kind of different point of view, which is really that when you look, in the stochastic differential geometry literature, they refer to the Nash embedding theorem. But at the end of this lecture, in the series of lectures, the things that you should know is that there are two Nash embedding theorems. There's one which is at low codimension, low regularity. There's one which is at high codimension, high regularity. Theorems are with very kind of different character, very different, very different proof techniques. And so, knowing something about Nash 1954 at this point, a natural question to ask is, can we use the same construction for isometric embeddings? So again, let me kind of just give you the intuitive conception of the question that I'm asking, based on our favorite examples so far. Let's say torus and sphere into R3. So let's just look, for example, at T2 into R3. So that's T2. And now we know that when we try to make, that there are infinitely many isometric embeddings of the torus. And so what we know is that we've got this kind of, really a rough object. And now the question that we're asking is, can you do, so here we know. Okay, so I'm preempting a little bit kind of results of Dominic, his co-authors, and kind of recent results. So we know here that So we know that there exists U which are C1 alpha embeddings. You know, U if there exists U belongs to C1 alpha embeddings. Such that. So G is the identity. So you've got this rough object sitting in space. Can you define Brownian motion on it? So you kind of want to use these theorems, or you want to use this construction. So the projection is actually nicely defined. So as soon as you've got a C1 embedding, you've got a well-defined tangent space, and so you've got a well-defined projection. When you've got a C1 alpha embedding, as we do, it'll turn out that your projection has a little bit of additional regularity, so the normals are changing continuously, but in a reasonable controlled way. And so let me just kind of I call that, so let's call this E equal. So in order that equal or have unique strong solutions, then you kind of look at standard SDE theory for existence of solutions to SDE, strong solutions to SDE. So, you typically want the drift, and, so let's say, let me just focus on the drift, the regularity of the drift for now. You'd like the drift to be Lipschitz. We need, let's say, the mapping from sigma to, let me just write it out as RQ, which maps little v to H of C to be Lipschitz. This is a curvature. Okay, so let me write it out this way. So H is modelly something like second derivatives of U. And so this implies that you need U in C3. So if I want to have, so my metric over here is C infinity, but in order to have solutions to the SDE, to standard SDE theory, you need regularity. You don't have regularity. So we have rough embeddings, and this picture, at least naively, does not apply. Yes?
But then what would be worth being called the Brownian motion?
That's the question.
Oh, right.
You're asking all the right questions, Arturo. You really are. So I'm setting this up on exactly for you. Okay. So look, I mean, it's one of those cases where, like, really, right? Like, I mean, I do my best to avoid estimates and regularity theory. So, I outsource that to my young, smart colleagues. But in some sense, at first sight, at least, when you kind of think about kind of modeling problems, right? Like mechanics, things of that nature, you don't kind of look at smoothness all that closely. You want to get kind of your fundamental principles right, and so somehow you want to get your equations right. So kind of thinking about this equation over here. But we see that when we study the Nash embedding theorems, you really have to do low regularity. This is forced on you by fundamental geometry. The existence of C1 alpha embeddings comes from non-existence. The kind of striking feature of the Nash theorems, the Nash 1954, is that there are unsmooth solutions. So embedding is a very, very natural construct, is a very natural concept. The existence of these embeddings is clearly interesting mathematical phenomena. You'd like to say that Brownian motion on these rough objects is for kind of natural reasons, very, a fundamental object. So recall that, like, the problem over here is coming about because we're working in the extrinsic space. If I just look at the torus over here, you can easily make a Brownian motion on the torus by just kind of taking Brownian motion on R2 and projecting that So it feels a bit like we're almost making an artificial difficulty. But it's not, because we are trying to understand the phenomenology of these critical exponents. So in the last lecture, Dominic ended with the threshold problem, where there's a threshold which separates behavior of solutions to these PDE. And so the question of regularity is forced on you by fundamental mathematics. You have to, I think we both would agree that Brownian motion on the manifold is a natural object. And I think at this stage, we've tried to convince you that low regularity embeddings are fundamental objects. So take a simple geometry like the torus, look at one of its embeddings. Can you do this construction?
And you cannot do it intrinsically in the origin manifold, right?
So you can. So there is an intrinsic construction. So let me state the theorem, and then let me give you a sense of where this theorem comes from. So the theorem actually appears in our paper as a corollary. But and let me even state it informally at this point. Perhaps because if I state it formally, I'll get confused myself. So, okay, let me do it. So this is actually it's corollary 5. It's corollary 2. So actually corollary 2 in now and 4. Because it's follows, so assume the metric that we begin with is C2. And U and G to RQ is C1 alpha isometric embedding with alpha in the interval 1/2 to 1. Then somehow you think you have an S, so somehow it is possible. So we introduce a renormalization procedure, which I will kind of explain to you. And as a consequence of this renormalization procedure, you get an existence of extrinsic Brownian motion on this manifold. So let me make some caveats. So the hypotheses of the theorem are not only, are kind of, let me put it this way. So we are actually assuming that U is C1 alpha. But when we look at the pullback metric is actually a little bit smoother. So here's a remark. So it's not something which is an arbitrary C1 alpha. It's not an arbitrary C1 alpha embedding. It's a C1 alpha embedding such that so this hypothesis may look very strange at first sight, but it's really reflecting the nature of the problem. So for example, when you're doing torus embeddings, the U can be rough, but when you pull back, the metric obtained from U, that's actually smooth. I'd love to say that this theorem applies to the torus, but actually we don't know that, and we don't even expect it, because we don't expect the torus to have an alpha which is in the range 1 to, so, but the theorem is not empty. Okay, so that's remark 1. There are, so let's say there are surfaces, so there are convex surfaces such that U belongs to C1 2/3 plus, and U sharp is C2. Okay, so there are actually non-trivial manifolds for which our theorem applies. And here's remark 3. And this really is kind of corresponding to places where we do need assistance from stochastic analysts. We do not know. So Z is constructed from a renormalization procedure that I'll try to explain. So this is something where I really feel like people for whom semi-martingales is their bread and butter. We do not know that ZT is a semi-martingale. So we do net in general. So this is true in the setting of remark 3. So there are certainly non-trivial examples of embeddings, rough embeddings, where it is possible to construct extrinsic Brownian motion. So perhaps not that hard, to give you a rough sense, what happens is that we smooth the embedding a bit and then we pass to the limit. That's how we kind of, it's a smoothing procedure that's used in these cases. So there are actual settings where we do know that what we're getting out is a semi-martingale. And this is very, very important because what you're really, again, as I said, what you're looking for is obtaining geometric concepts from probabilistic grounds. And the geometric concept over here is mean curvature. And we're trying to kind of provide a notion of mean curvature for rough embeddings. And so there is a setting where you get the mean curvature in this way, or a generalized mean curvature in this way. And it's really, it's exactly corresponding to the Dubin decomposition of the semi-martingale. So we really need this theorem in general. We know it in certain settings. And so it's kind of one of these places where, like, please somebody take a look at the details and see if that. So what's really going on is that we're using certain limit theorems, which are navigable again. But there may be I'm sure there are kind of finer limit theorems that are known in the, let's say, the Jacquard-Chiryaev world, which I hope will apply in this situation, but I certainly don't feel competent to look at that. So it's kind of, I just want to kind of give you this part of our work in kind of, let's say, the most intuitive form, just to highlight certain aspects of our work that are open and I hope are accessible to kind of like anyone looking for an entry point to this sort of problem. There are very, very basic examples of surfaces, interesting embeddings of surfaces, and we really need kind of real probability theory over there. So yeah, just one last remark. So again, with it's not quite, so with the torus, we don't quite know this. It is possible that our construction will generalize even to kind of alpha less than 1/2, but our proof technique that's over here really needs alpha greater than 1/2. And this proof technique actually goes exactly to a kind of key technical idea in kind of the work on Euler. So it's kind of like this kind of beautiful kind of back and forth between turbulence and embedding. And so kind of in the work of Delevis and Sekahidi, what they used is these techniques of Nash, this, the kind of breakdown into primitive metrics, so analogs of these ideas for fluid mechanics, the subsolution breakdown into these fluctuations. So those ideas were used in kind of the approach towards the Onsago conjecture in fluid mechanics. And conversely, there were technical tools that came from fluid mechanics back into the embedding world. And one of them is the use of commutator estimates. So this structure over here, the fact that you may have something which is rough, but there are still sufficient cancellations in the first derivative. So to get this right, you need a commutator estimate, very classical commutator estimate, but that's also kind of a key piece that's living under the hood over here. So there's a bunch of, in our paper, we state the results, and then there are a bunch of remarks that kind of explain the kind of key technical ideas, because there's a kind of interplay between probability analysis and geometry that's used over here. And so this is kind of one of the key technical bases. Yeah, so.
I was curious on number 2, why is it important for the surfaces to be convex or unconvex?
Yeah, so again, so let me remind you about the kind of 3 basic examples that Dominic gave you when looking at the embeddings of 2-dimensional manifolds. So there are cases where there are no embeddings. So if you look at the torus, or if you look at the hyperbolic space, you do not have embeddings. So that's in the rigidity in those problems corresponds to non-existence. But then there was the embedding of the sphere, or embeddings of, so the Weil problem, so where you've got something just topologically the sphere, but with a metric which is positive. So those correspond to convex surfaces. So in Dominic's picture yesterday, there was C1 non-existence, C2, so it's kind of like flexibility, rigidity. So if we put ourselves in the convex case, rigidity over here means uniqueness of solutions. So think about embedding the sphere. So, like, it's kind of like unique up to, so somehow, and then when you go down to C1, you've got kind of very rough embeddings. So over here, what happens is that you can push the rigidity down to, I don't know, if that is 2/3 the correct exponent. So you can push down to rigidity, you can push up for flexibility. And so I think Dominic will be talking about that. So this is very, very special and convex surfaces. So two-dimensional convexity. So this is very, very important. And this relates to classical work in geometry of Pogorelov. So there's a Russian school, Alexandrov. So really thinking about convexity. So that's where it's coming in over here. So you can kind of see like the convexity over there will play naturally with convexity in kind of martingale theory. But that's one of the things that's going on.
Just a remark, you can easily push this. I mean, there are convex surfaces such that U is also C1 1/2 plus.
Okay.
And
So,
I mean, you could replace 2/3 by 1/2.
Okay. So I think then we need to edit the paper to put that in before resubmitting. So okay, maybe we can go down to 1/2 plus. So yeah, I mean, so look, I mean, a lot of it, in some sense, I feel like part of my aim, right? Like, so thanks very much for your hospitality, but I did have very selfish aims in coming here, which was to introduce you to this class of problems, but also to point out that there are pieces of it that are still opaque to us. And some sense to actually understand, or even to understand the statements of theorems, to kind of want to look at these questions somehow requires there's a certain barrier to entry in terms of kind of just the question. So let me just kind of give you let's say just a cartoon to give you a sense of how we were thinking about these theorems. Because it's not just the existence of the CT, but you really kind of want to understand. Let me go back to the cartoon of curvature as a constraining force. Just to give you a cartoon, to kind of relate it to these remarks, but also to kind of relate it to kind of stuff that you guys know. So let's just recall Tanaka's formula. So let's assume given standard rounding motion. And then let's look at this mapping from the real line to the real line, which takes x to mod x. So the Lipschitz, definitely not C2. So of course we know that Ito's formula should not apply because it's not C2, but you know that you've got a replacement. And so we know that, let me write it out as du, let's write it out as du. What do I want to do? Let me write it out in Hans way. So let ZT be U of BT. So of course, I'm just using the U to kind of remind you, like, you don't think about Tanaka's formulas have anything to do with embeddings, but this is actually an isometric. This is a kind of isometric map from the line into the line because you're just folding and you're maintaining lengths. So you're taking an isometric map with a singularity. And so I want to think about it. It's not an embedding, but it's an it's an isometric immersion, I guess, except for 0.0. So it's something which is preserving length. So actually we can think about it in my world. And so if I look at this stochastic process, then what I know is that ddt is just by definition that. And so that's the first derivative plus the local time. So I just want to think about it in relation to kind of the intuition that I gave you of Brownian motion earlier. Let me just make a graph and picture. This is, let's say, x, that's mod x. And so, here's an isometric map of R into R2. And let me smooth this out a bit. And so let me look at, so let's just look at that's called. So, let me look at a given Brownian motion, and I'm looking at its absolute value. So I'm looking at a point which is kind of moving along this curve. And if I smoothed out my curve like that, I have a smooth curve sitting in R2, and my earlier construction of Brownian motion would work just fine. And so if I look at Brownian motion on the smooth curve, then I know that it's kind of got this mean curvature. It's kind of pushing me and keeping me on this curve. And so the beautiful fact about Tanaka's formula is it's telling me that this picture somehow persists in the limit. You've got a Brownian motion which is moving around on here. You hit this point and there's a kick that takes you from one place to the other. So the intuition of a smooth constraining force has now been replaced by kind of random kicks to keep you on this guy. Okay, so I can begin. So I'm kind of thinking about Tanaka physically as the local time is kind of hitting me and keeping me on this map. So the reason we care so much about this piece of the puzzle is that what we'd like to do is to if we knew that dt is a semi-martingale, so now but this is for C1 of magnetics. I'm just going back, so this was a kind of aside to kind of just tell you that you can think about Tanaka's formula in these kind of geometric kind of. I'm kicking you to stay on this Lipschitz embedding picture. So somehow if I knew that CT were a semi-martingale, then what I would get is dCt is going to be a martingale term over here plus, sorry, let me use my notes. So actually did it slightly differently. But what I'm trying to do is to kind of, so this would be, okay, let me say the martingale term plus, I don't know, whatever the replacement is for the Tanaka term. So,
the local sign?
well, I shouldn't call it the
variation.
replacement for mean curvature. So, okay, let me step back. I'm saying too many things and kind of messing up. So what I said at the outset was that if I look at smooth embeddings and I write out the equation for extrinsic Brownian motion, there's a constraint which is given to me by the mean curvature. So now I'm in the setting of the rough embeddings. I don't know in general, but I do know in special cases that the process that I'm getting out is a semi-martingale. Since it's a semi-martingale, it's got to do Meyer decomposition. So there's some term over here. In this particular case, I know that this term is a local time. So in a sense, the reason that we're kind of looking at this replacement for the mean curvature has to be some sort of geometric analog of something like a local time. So it's kind of like, okay, you've got this rough embedding, you want to make a stochastic process that's living over here, but the stochastic process is probably getting kicked at different places. So your embedding may have little spiky bits, and so your stochastic process is going to get kicked at random places. And so that's a concept like we would really like to get right. So we know that this correction term exists in these cases, but somehow we'd like to believe that it's there in general. And what that requires is actually a strengthening of our limit theorems into a semi-martingale limit theorem. Okay, so for people who know stochastic analysis, this is something where we'd really like some insight. Okay, so let me just pause at this point. Yes, yeah.
You have explicit expression for H in terms of the U, right? So the problem is that you cannot take second derivatives, but you insist of symbolically putting them. I mean, if you're working with these guys, you can think of them instead of derivatives. You can think of them as symbols and realize them as generalized functions.
So, okay, but the devil's in the details in that, right? Yeah, so that's exactly right.
Generalized functions, and what you're doing over there is a convolution. So you can try to, in the same way in which you are trying to define, like in Tanaka, what's working out really is that if there's a pulse, it's not a function, but you could try to qualifying.
So, okay, So let me step back and say, like, in many ways, like, so it turns out that in order to get the existence of the ZT, I have to tell you a couple of other theorems. And then there's a modification procedure which allows us to construct the ZT. So it's completely true that there's a modification procedure that you use to get the ZT. The modification procedure actually is kind of more subtle than a kind of naive modification. But let me just say that I'm trying to communicate over here the intuition in terms of where this is coming from. Okay. So this is one of the, I think this kind of contribution, this is a contribution that I really like, and really just comes by kind of looking again with close eyes at the kind of classical results in stochastic differential geometry and kind of putting them, recognizing that you do have to get these results at low regularity and kind of recognizing that kind of there's this very kind of unexpected interplay between the probability theory and the embedding theorems. Okay. So that's actually half the story, but now let me give you at least in the next 30 minutes kind of where this stuff comes from. And I'm going to focus on, let's say, the conceptual part because it's a little bit easier to explain on the board. But in a sense, also to kind of show you that the conceptual piece is involving, in some sense, again, exactly in some sense, following the path of the 1970s in terms of recognizing that the extrinsic construction is unsatisfactory on kind of the fundamental grounds that it is extrinsic, not intrinsic, but kind of looking again at the intrinsic construction and saying that actually even the intrinsic construction, when you look at it carefully, there are new things to say, and in particular, a precise relationship with the isometric embedding problem. That's one part, or one of the things I really wanted to show you guys. And now let's step to the next part. And I'm not going to kind of do the details of the intrinsic construction because it involves a bundle of frames and kind of fancy geometry. But it's kind of described in the introduction to our paper, and I can give you an intuitive picture of this. So, now let's look at intrinsic grounding motion. And again, let's look at the intrinsic grounding motion, but let's also look at isometric embedding. Okay, so just as kind of background, yields will be Menon. So what yields Elwood and Menon did in the 1970s is to provide an intrinsic construction of grounding motion. You do not use an embedding. And roughly what it goes, the way it goes as follows is kind of given So given this manifold, we want again an explicit family of SE. So my XT is always Brownian motion on the manifold. So it's a probability measure on the path space of this manifold, whose law is equivalent, whose law is described by the heat kernel of this manifold. But somehow what you want is a kind of geometrically natural construction. So you can imagine that there are many constructions of Brownian motion on a manifold. So for example, you could take random walk type constructions where you kind of move along geodesics, take short steps along geodesics, and then pass to the limit. This is a different construction. The way it goes is somehow a little bit sophisticated. So somehow, let me just give you a couple of key features. So you're looking for a stochastic, you're looking for a diffusion whose generator is the Laplacian. I just need to kind of write out again the expression for the Laplace Beltrami operator. There. So XT is diffusion with generator G. So let me just write out the expression again for the Laplacian G. I do need this because we're going to kind of make statements about regularity. So take a C infinity function on the manifold. And the Laplace Beltrami operator is defined by, so I'm going to use slightly different notation from the last lecture. Where and GIJ University. And in coordinates, the kind of the equation that you want for the associated diffusion is d xti equal to g w. I'm using, did I use W earlier for my Menon process? So then we will use D. Okay, let's use W. There we go. And so we will kind of need to do regularity. So BI is 1 over read anymore. E G G G and G. And the relationship between sigma and the G is that sigma and A, sigma G. K a repeated sum over indices. So somehow, given the metric, the inverse metric corresponds to the leading order term in the kind of elliptic operator that we have. And the noise is determined by the square root of the inverse metric. Okay. So this formula is actually quite valuable. If one goes back and looks at, for example, Bharathan's first paper on large deviations, he actually begins with the second order elliptic operator and recognizes that every second order elliptic operator can be thought about in geometric terms, in terms of metric. So somehow this is what we're looking for. So somehow this is the type of SDE that we're looking for. But we must remember that we're working on a manifold. So somehow SDE expressions of this sort have to be kind of taken with a pinch of salt. So in particular, if you're trying to find Brownian motion on this manifold, you need to ensure that you've got sufficient regularity so that you've got strong solutions, so that when two coordinate patches overlap, you have uniqueness of solutions. So these are regularity assumptions that are not used or not kind of discussed in the classical literature because everyone assumes that G is C infinity. But when you actually look at the intrinsic construction, again, carefully, with the eye towards reducing the regularity of the metric, which is something that's very, very natural when you come at it from the kind of theory of the isometric embedding problem, you realize that even the classical theory on kind of construction of intrinsic Brownian motion, there are kind of places where suddenly you begin to see kind of new phenomena appear. Okay, so what you're looking for in this world is, so somehow if you just view the problem analytically, we've got a Laplace-Beltrami operator, which is described explicitly in coordinates. Associated with the Laplace-Beltrami operator, think about this as the, as the generator think about these as kind of giving you a second order elliptic operator, and think about going, taking a second order elliptic operator and looking at the associated SDE. So this would be kind of, let's say, standard SDE theory if you just think about it in terms of an operator. And from the theory of, from the standpoint of SDE theory, you think about the regularity of the metric and kind of the regularity somehow notions of the associated solvability of the associated elliptic equations. But somehow you want to combine this picture with a natural construction of SDEs. Okay. So to cut a long story short, what Ilse-Elworthy and Malyavand did was to formalize an idea that went back to Bochner. And Bochner's idea is an idea that I like very much because it corresponds to, I would say, the fundamental technological invention, which is the wheel. And so you look at the kinematics of a wheel. This really pleases me. I was a mechanical engineer. So, there's an equation for how a wheel works. So when you move a wheel, the construction is called rolling without slipping. You've got the wheel, wheel moves in that direction. So, and this point stays fixed. So somehow when you've got a wheel, it's moving in that way, and it's rolling without slipping. And so Bochner's construction let me just switch to intuition at this point, because I think otherwise I'm going to run out of time. Yeah, 4:15. So I'd like to at least get to our main insight in 15 minutes. So I can't do too much detail, but now, you want to make Brownian motion of this manifold. You want to do it in a natural geometric way. These are the equations that somehow you have to get right for your final diffusion. But here's how you want to think about where this construction is coming from. So imagine that you've got the sphere, and you want to make Brownian motion of the sphere. So what you do is you take the plane and assume that on the plane everywhere there's ink. So now you assume that you've got a Brownian, okay, let's use yellow. So somehow in all of these problems, you want to assume always that you're making Brownian motion on a standard space. So here I'm working with an n-dimensional manifold. So let me assume that I've got an n-dimensional plane and I've got a standard Wiener process. So here, let's say, this two-dimensional plane, and I've got a standard Wiener process in 2 dimensions. So now what I do is, in order to get Brownian motion on the sphere, I take my sphere, and then I roll it along this path. So you kind of keep moving the sphere along this path. And as you move the sphere along this path, at the end, when you pull out the sphere, you get the ink on the sphere. Okay. So this is the geometric intuition. This geometric intuition is formalized with the bundle of frames. And you can write out a standard kind of system of stochastic differential equations. So Ikeda and Watanabe being the best reference on this, which gives you Brownian motion by kind of formalizing this construction.
Is this heuristic in the paper? Or?
This heuristic is there. It's not in the paper, but the heuristic is in Ikeda Watanabe. Okay, so I don't know what the actual original source of Bochner's thing is, but like this construction is actually, so yeah, let me state this because this is actually very, very important. So when one looks at the theory of stochastic differential equations and stochastic flows on manifolds, one of the pieces in relation to the work that we're doing is that these geometry theorems involve starting with the differentiable manifold. When you've just got the differential manifold, you're just doing manifold theory, and then you augment your manifold with additional structures. So the theory is that if you've got differentiable manifolds, you can always do SDE theory on differentiable manifolds with no additional structure using the Stratonovich SDE. If you want to get martingales on your manifold, you need to add on the additional structure of connection. If you want to get Brownian motion on your manifold, you add on the additional structure of the metric, and you take the connection that goes with the metric. So there's a portion of SDE theory which is super robust on manifolds. When you kind of begin to get geometrically precise SDE theory, you must add on additional structures. And in a certain sense, I see our work as kind of being one of the first steps in this direction, where you combine these geometric insights, which actually are extremely well known in the stochastic differential geometry community, with kind of precise regularity theory, because we know that there's a kind of sharp interplay between the regularity theory and actual geometric phenomena. Okay. So now let me get to the kind of core insight that underlies our main theorem. Oh, I should write on that. Okay, that's fine. Let me just summarize this. Summary. There exists a canonical intrinsic notion on MG on, call it now intrinsic probability space. So where the processes, corresponding. So this is the Wiener process with exactly n driving noises. It's defined on a particular probability space. I'm going to call that the intrinsic probability space, because when I'm making Brownian motion extrinsically, that's a Brownian motion living in RQ, and that's coming from another probability space. So we've got two constructions of Brownian motion corresponding to two different probability spaces, and these two different probability spaces, can naturally be thought of as intrinsic and extrinsic. So at some level, our work relies on kind of now drawing a couple of pictures, forming a soft theorem or a soft way of looking at isometric embeddings probabilistically, and then pushing it technically down to low regularity. So I do the soft stuff, Dominic does the hot stuff. I should be clear at this point in these lectures. Okay, so let's make a comparison. So assume so let me not make any smoothness assumptions beyond. So let's say use a. Let's just start with use an embedding. Let me just make a picture, then let's make the smoothness theory precise. Okay, so let me go back to one of the basic pictures that I began with. So here's our abstractly defined manifold. We'll fix a standard point X. And we have a Brownian motion, capital XT, starting at that point X. Now we've got an embedding, and that's our image of our embedding contained in RQ. This point X, let me call that reference point B equal to little UN. And so I'm going to push this process forward. I'm going to call that YT, which is U of X. So I've taken my interior construction and I'm just looking at its image in this space. On the other hand, I also had another process. I need a more striking color. Get this artistic piece right.
Yes.
That purple? No.
Berkeley.
So let's start out first with a C infinity embedding. And so you see that I've kind of got two possible constructions of Brownian motion on my map. So I think the way, if you look at the ST stochastic differential geometry literature, you kind of begin with the extrinsic construction to orient yourself. And they are like, well, this really doesn't work. Like, what you really want is the intrinsic construction. Well, but, a priori, let's just look at these two processes. And we kind of see that, clearly if this somehow both of them correspond to the same Brownian motion or correspond to kind of processes with the same law, then despite the fact that you've kind of constructed processes on two different probability spaces using two different recipes, both of them should somehow have the same law if the process is isometric, if the embedding is isometric. Okay? So that's actually the theorem. It is in the C infinity case. Let's just assume everything is C infinity. That U is an isometric embedding. So U is a solution to our nonlinear system of PDE. If and only if YT and ZT have the same law. Okay. So isometric embedding is characterized probabilistically by equality in law of these two constructions of Brownian motion. So in some sense, if you're thinking about this stuff, like this theorem is not unexpected, but it was not formalized in some sense before our work. And in some sense, we use this formalization as the foundation. So I'd like to relate this back to something that came in the first lecture. So first of all, what we've been doing so far is analysis. So I give you an isometric embedding, you make these constructions. Okay. So everything is C infinity over here, my U, my G, everything. So if I give you an isometric embedding, then you can kind of certainly believe that YT and ZT have the same law. It better have, because that's exactly what the metric means. So the issue is where to get the converse from. Well, the converse is actually Vardhan's lemma. So you have heat kernels. So when I say that these processes have the same law, what I'm saying is that they have the same heat kernel. And what I told you in the first lecture is that if you are, maybe in the second lecture, I'm not quite sure, but if you've got the heat kernel, you can recover the metric from the heat kernel by Vardhan's lemma. Okay. So, in some sense, the forward direction is natural. Actually, both directions are natural. So the forward direction is actually construction. And the backward direction is Vardan's lemma. Okay, so if these two processes are have the same law, then this implies the same heat kernels. So, take 2 points over here, take the bridges between them. So the probabilities of these bridges are going to be exactly the same. So somehow let me make again that picture. So let's start D and D prime. So the probability of bridges between these 2 points is given by a heat kernel. And we know that the limit at equal to 0 of minus 2t log kt dv prime is going to be the geodesic distance between these 2 points. So when limit, these guys are just going to converge to geodesic. So you can recover geodesics from the heat kernel, and that actually means that you can recover isometry from equality and law. So in principle over here, I'm solving a PD. But what I've really converted that to is a purely probabilistic statement about equality and law. So it's kind of relaxation of the PD. Yeah.
If you had short depths, would there be any?
No, it's okay. No, the idea of shortness does not appear in this theorem at all. The shortness is really related to the construction of the isometric embedding theorems. It's related, of course, because what we really want in our main theorem is really an extension of this idea to the low regularity setting. Okay, so I'm not quite sure how much time I will have. So I'm actually at the end. So let me kind of, I'm not sure how much Dominic will cover, but actually the main result is you start with this starting point, and our main result is actually that this construction works for C1 alpha embeddings and C2 metrics. And there are several different pieces of this, each of which is kind of an enhancement of kind of ideas. Okay, so let me at least state that. So kind of the main result actually is not this one, but this is really just an observation, which is the empty level result. But the main result, and this is theorem 4 in our paper. Same holds. I'm sorry, this is a little bit too informal, but same holds for G belongs to C2 and U belongs to C1 alpha, alpha in 1/2 1. So the structure kind of persists. And in fact, we use this theorem. So this theorem is actually important even for kind of the renormalization, which I'm kind of referring to in the Tanaka piece. So I'm sorry, in my head, I thought I would be able to explain the key ideas over here, including these pieces. But actually, just this statement involves kind of replacing the standard intrinsic construction of Brownian motion with the martingale problem. I'd like to say that we don't know if G belongs to C2 is sharp. If you actually look at the generator associated G, if you look at the Laplace-Beltrami operator, let me actually just write that out because it's important. I will pull up immediately after that. Just give me 5 minutes more.
Sure.
Because this is kind of the main point of everything. So I'll just kind of do it again. Yeah, let me just look at the expression for, right, so. Maybe I'll just kind of go back to my, right. So let me write out my SE again, because I want to make some remarks on regularity, just so that you guys see again a kind of bottleneck where we think the theorem should be improved, but we don't quite have it. So this is the SD, which would correspond to intrinsic Brownian motion. And now we just want to look at it from the standpoint of regularity to see how much smoothness we need. Yeah, chains. We have a chain. And okay, so let me just make a remark on the regularity of the metric. So G is C2. We're looking at the regularity of these pieces. So the sigma ij over here is really just a square root. So if G is C2 and strictly, satisfies, is strictly bounded away from 0, as is going to be in the case of closed manifold, then this is going to be a C2 function. And so your sigma over here is going to be a C2 function. If you look at the B, you're differentiating the G's once. Okay. So this is going to be a C1 function if the G is C2. But if you look at this term, in order to really kind of just have a well-defined term over here, it seems more natural to have this guy just be C1 so that this term is bounded. So C2 may not be sharp. So it turns out that in order to just define intrinsic Brownian motion, you're pushing the regularity down. C3 is what you get from kind of cheaply from the standard theory. And so what we really proved as a kind of way step over here is that intrinsic Brownian motion, the martingale problem is well defined when G is C2. So our estimate for the martingale problem requires actually a C1 convergence and a C2 limit because of a particular tightness estimate. So again, it feels like somehow there should be space to play over here, where G being C1 may be enough to get an intrinsic construction Brownian motion, but we're not quite sure. Nevertheless, our theorem holds in this setting, so you have to make an assumption on smoothness on the metric. You have to make an assumption on Hölder regularity above a critical threshold. So the kind of alpha is equal to 1/2 kind of conjectured by Gromov kind of appears over here in certain natural ways. And let me kind of give you the main conceptual insight. So, when I began with this project, somehow I began with the technical goal of improving an exponent in this problem and kind of being related in some way to turbulence. So as I've thought about more and more about this problem, as I've kind of seen more of the probability kind of fit in technical pieces, I felt in some sense kind of that conceptually our work is getting closer, even if it's moving technically a little bit further away from kind of the way we've thought about Nash's work traditionally in analysis. And I'd like to just kind of conclude, the kind of series of lectures with kind of highlighting, which for me is kind of really magical about Nash's work and kind of this entire circle of problems, is kind of the interplay between concept and technique. So at some level, you have to be faithful to Nash's techniques in order to actually improve these theorems, right? So somehow these theorems have been around for 70 years, and they're really just kind of amazing pieces of work in analysis. But the problem with these theorems is that, in some sense, there's an arbitrariness of the construction, right? And in some sense, it seems kind of divorced from the physics in the sense that when we use these theorems to construct solutions to PDEs, we think about these solutions to PDEs as being unphysical. Counterintuitive solutions to the Euler equations which dissipate energy, which kind of do nightmarish things. So they call wild solutions for a reason. So on the other hand, when you look at Nash's work, Dominic kind of began with kind of Weil's description, which I really liked, of embedding as being realizability of an idea. So Weil's work is actually coming from Einstein's work. So what Weil was doing is really kind of trying to really look at kind of Einstein's work and recognize the importance of an observer in a physical theory. So for me, what's so important about kind of the use of Barzan's lemma, the use of the terms extrinsic and intrinsic, reflects in some ways exactly kind of trying to match more carefully the geometry of the problem of the manifolds, the kind of geometry and the analysis of the embedding problem with the fundamental physics and the role of the observers. So I see Barzan's lemma in this problem as formalizing somehow the concept of how do you measure length. So for me, the way you measure length is through a statistical experiment. So the statistical experiment is formulated precisely on a probability space. So the concept of measurement can be formalized only through probability theory. So in some sense, what we're really saying over here is a mapping is isometric if and only if two different observers measure exactly the same lengths between every single pair of points. So this kind of idea is related to kind of thinking about the embedding problem for a framework of information theory. And so kind of what we've been doing in this entire project is kind of me coming up with this, okay, how do you fit these ideas naturally with physics and kind of, working with the analysis and kind of what's known about the stochastic differential geometry to kind of formalize this idea. So there are several pieces of the puzzle, some which are technical, some which are, in some sense, this framework is for me the first place where you really see probability theory as being completely fundamental to the isometric embedding problems because it's formalizing the concept of the measurement of length. If you think about Nash's work, it's actually an outgrowth of work beginning in, let's say, the early 1800s in terms of the notion of space. So Riemann's fundamental idea regarding the metric is also Riemann's fundamental idea formalizing the concept of curvature. So what I really liked about this project is that somehow we are getting at the concept of curvature, mean curvature. So we're still not at kind of intrinsic curvature, but at least with the concept of mean curvature, we're getting it on strictly probabilistic grounds based on the idea of measurement. And so for me, that's really, at least at the conceptual level, the power of the work. And there are just problems galore for everyone. And so thanks very much for your attention and sorry for going over time.
Gracias. Thank you. Questions for Govind? Questions?
Let's get coffee. Let's get coffee.
Thank you. We thank you again.